All right. Now, today's talk will be about PID controllers and the model matching controller. Before the exam, we've talked about this, but today we will have a special system under consideration. Now, as usual, we have settling time and overshoot values as specifications for the closed loop step response. And the first task is to design a PID controller using the tabulation method, which we all already know. But then, interestingly, instead of using the tabulation method, the question here asks us to propose a PID controller. This seems to be interesting because we have a tabulation already in A, but still it asks us to propose a PID controller. Now, other than that, in C, we have to propose a controller. Now, here, the type of the controller is not even limited, so we should propose a controller, PID. It doesn't have to be a PID controller. And then we have D, where we are going to use the model matching method to design a controller. And we have a very basic system here with coefficients 0.2 and 25.01. So let's dive into A and just use the tabulation method as usual and come up with a PID controller. And hopefully we will see how to propose a PID controller, if it's possible to come up with a better one. So now I have already defined the transfer functions here. I have the specifications. Since we have both specifications, the settling time and overshoot, we can directly go ahead and look for the overshoot formula to calculate the overshoot here. So that's that. Now we can use the settling time info to come up with omega n value here. Since we know what TS is and zeta is, this is the formula. Now, so far we've actually designed or decided on two basic poles, the dominant poles. Now, our system is a second-order system, so in the closed loop we will just need one pole, one additional pole here, the residue pole. So according to this, PDS should look like S squared plus 2 times zeta times omega n times S plus omega n squared. And PS should look like S plus P. Pretty basic. Now, let's also define KP, KD, and KI. They are real values. And as always, we should use these coefficients because I'm going to use the algebraic methods. Therefore, this is a good idea. Don't use the pole zero representation. So let's define KD times S squared plus KP times S plus KI divided by S. And as usual, the closed loop, which is Fs times Gs divided by 1 plus FSGS. So now we need the numerator and denominators. I'm going to call them PZS and PCS because this will be our zero polynomial. This will be our characteristic polynomial. So let's use num then. So this is pretty basic stuff up to this point. I'm going to look for the coefficients of PCS. And I'm going to normalize it in case there is a coefficient in the highest order term. So I'm going to normalize this. So there could be the case where we have 4s cubed, etc. So s cubed plus something. Therefore, I should divide all the coefficients by 4. Or I can also multiply PDS and PS with 4, but this seems to be more clear. And then we have the problem where we equate the coefficients, PDS times PS, and all the S coefficients here. So that's that. For sake of readability, let me go ahead and cycle through each equation in the equation set. And Let me display them. So nothing new. We've covered this already. Now we have three equations, and it seems to be that we have four unknowns. So having four unknowns and three equations tells me that we could use the tabulation method here. So let's do that. But examining these set of equations here, I can choose one of the controller parameters as the free parameter. Let's take ki, for example, as the free parameter. And if you are using pen and paper, it's also possible to just come up with the parameterization here, because all are depending on P here. Right-hand side is depending on P. And I can just work out what KD looks like in terms of P. And I know the relation between KI and P. Therefore, I can work out all the controller parameters in terms of P or KI. So let's use MATLAB for that. So let's solve this problem. But we have to specify the parameters that MATLAB should look into. So for example, I'm going to look for P, for KP, and let's decide KD. So since I didn't mention KI, and I've only three equations here, I've assigned P, KP, and KD here. So therefore, MATLAB will try to come up with P, KP, and KD in terms of KI. So at this stage, I can just get the solution of P, of KP, and of course, KD. So let's run this and see what we have. So we have FP, or P, parametric P. Okay, FP. So we can see that there is a certain coefficient times Ki. And if we remember the fact that the closed loop should be a stable closed loop, all the poles should be on the left half plane. And since we decide on PDS, we can see that P should be positive. Therefore, if I'm choosing Ki as the free parameter, Ki should also be positive, because if Ki is positive, then P is positive, and vice versa. So therefore, Ki should be a positive parameter. Now, I don't have to really look for FKP and KD for positivity, because I'm going to look for all the possible PID controllers here. So once we have that, what we can do is we can create a table that has certain results, and therefore I can choose a vector of Ki. And since I know that it should be positive, and that's the only necessity that I should satisfy here, I can go ahead and look for a vector that starts from 0, for example, stops at 10, has 100 points in it. So just a Ki vector here. And therefore, I'll need a table here. And I should have as many rows as I have Ki values, because each row will be assigned to this Ki value. Therefore, the length of the Ki vector here determines the number of rows, and then the columns. Now, for the columns, what I should do is I should first specify what I want to save into the table. For example, KD, KP, KI are the controller parameters. Let's save them. And then we could look for the settling time that is calculated using step info, and also maybe overshoot. And we can also have the first error, the second error, and combined, because this will be the thing that I'm trying to minimize. Therefore, we have 3 and 3. I guess 8 is the number of columns here. So now for each value in the Ki vector, I'm going to do the following. Now, I know what Ki val at each iteration here should be equal to. So I'm taking one element of the Ki vector here. And since Kp and Kd are depending on Ki, what I can do is I can just substitute into them. So let's say Kp val. Let's convert it into double and substitute into FKP instead of Ki, Ki val. and repeat this for KD. Of course, not here. This one here. So at this point, I have already the controller parameters for each iteration here. By the way, I'm not checking for P because I've just manually examined it and I've concluded that KI should be positive, and that's really it. So I don't really have to keep track of P. So now I know what the controller should look like. Therefore, I can directly define it. So this is the PID controller that I'm choosing in this iteration for this KI value. And it is KD val, KP val, and KI val. Now at this point, I'm going to look for the closed loop here. Fs times GS, comma 1. And then I will have info, look for step info of TS. What else do we have now? I needed to look for the settling time. So info dot settling time overshoot info dot overshoot divided by 100. You can also multiply this OS with 100 because I have divided into 100. I'm just going to do the same for this one here. And the first error that I'm going to calculate will be the absolute value between the settling time that is calculated experimentally and I have TS. I'm normalizing it with TS because TS is the actual value that should be set to. Let's repeat the same for overshoot divided by S. I can multiply by 100. I can just skip that. It depends on your choice. And then let's combine them equally. So 0.5 times E1, 0.5 times E2. So that's it basically. Now let's save them into the table. So table, the ith row, all the columns should be equal to the following. Let me just directly copy this here. This should be KD val, comma KP val, comma KI val, TSE, OSE, ERV, ER1, ER2, and ER. So I guess this should get rid of the task. This should do it. Let's, by the way, reduce the number of points for performance. Now, once I'm done, once I've stated all or filled in the table here, I'm going to look for the minimum column or the minimum row in this last column of this table, because that's basically the optimization or costs here. So therefore, I'm going to retrieve the index because I'm not really interested in the value of ERR. I'm just interested in which row is the minimum row here. Therefore, I'm going to use minimum with the function min with two output arguments here. It can give you the value and the index. So, and I'm going to provide all the rows in the last column. I'm just specifying all the rows, but the end column here. So once that's done, I can retrieve the whole row that I'm interested in. That would be the index row and all the columns. So basically, this is copied over here with the index that is the index where the minimum of this occurs. So at this point, I can also, again, repeat this whole step here, which we really don't have to, but I'm going to. So here, and instead of specifying these three parameters like that, I'm just going to pick the first three rows, columns of this row. Because I have saved KD, KP, and KI in order, I can just choose to do this. Now, at this point, we have already our closed loop, our controller. Let's create a figure that hopefully helps us in understanding the results. So as usual, let's have a subplot here. Hold on. And let's look for the R locus of fs times gs. Now, usually what I do is I get rid of the controller gain here. I'm just adding the zeros to the system, but today I'm feeling a bit lazy, so I'm going to keep it like this. The only difference here would be the fact that if you're using the root locus, if you click on it, you should look for the gain 1 because the gain is already included. So that's the only thing that we should keep in mind, but that's also not really important because I can go ahead and calculate the poles and zeros of the closed loop, the resulting closed loop. So I'm going to do that and plot it on top of it. So I'm going to plot the real values of poles, imaginary values of poles with a line width. And let's repeat this for the zeros. For circles. And that's basically, we have the root locus and we have all the pole zeros, all the resulting pole zeros. For subplot 2, I can also use sgrid, by the way, for zeta and omega n here. So I can see where the dominant pole pairs are. Now here, I'm going to calculate the step and plot it here. And that's basically it. I can also have a little info message here on the settling time. I know that this is TSE, of course, and then overshoot string maybe 100 times on SE. There we go. Let's run this. I guess settling time has capital T here and here. No. So there we have this. Of course, this is not the optimum. So let me change it to, I don't know, maybe 300 with 400 points. Yeah. Let me also check this one here. Anything else? Nope. Okay. You can also see that it takes quite some time, and we also did again forget something here. Yeah, that. So let's run it again. Let's increase it a little bit, maybe. So there we go. Now, we can also see what the table looks like. So Vpa table like this. Now here we have KD, KP, and KI. And then we have the settling time, the overshoot, and the corresponding errors, and then our performance index here. Now we can see that it starts with a huge value. It drops down to a certain point somewhere here, and then it starts again to increase. So this is our optimum index here. By the way, what we can do is what I almost never do, but what we can do is we can do the following. Let me create another figure here. We can plot the table all rows plus index because this is kind of the objective here, so we can see what we're really looking at. Takes quite some time. Here we can see that, even though it's not really that obvious, we can see that we have somewhere here a minimum here. Now, there we go. Now, since we are using tabulation, we should be aware that we might miss some global minima here. We might be stuck in local minima here. But therefore, in order to try to prevent this, we should have a finer grid, so more and more points in this KI vec here. Hope that I can show it to you. So we need a large interval with as much as points as possible here in KI vec in order to not miss this global minima here. So yeah, that's not really important in this case because we can see that the resulting optimum solution here has an interesting step response, first of all, because the question does not mention what type of system we're dealing with, but we could just think about motion systems, for example. If you're in a vehicle and you are trying to accelerate here, the thing that happens here is that you accelerate with a small time instance with a huge acceleration here. And at this point, you drop a little bit. You don't really accelerate, and then you decide to accelerate again. So this is kind of weird in terms of vehicle motions. But it might be making sense for fluid systems, for example. If it's the height of the fluid in a certain cup, then you can see that it rises, it falls, and then rises again. So yeah. Now, in terms of PID controller design, it seems a little bit odd because we have a set of zeros in the domain, in the dominant region. And then we have our set of complex conjugate poles that should be dominating. And then we have another pole. Now, in terms of dominance factor, it seems like this one does well, but we have these two zeros here. And let me remind you that you as a designer have placed this set of zeros here. So we should blame ourselves here because we are the ones that, who place these zeros in the dominant region. Because the controller has zeros, the system does not. So this is an example which shows us that even though we are satisfying the settling time pretty well, we don't really have the best overshoot here because we were looking for 10%, but we have 2.4% overshoot here, which is not ideal, but we can maybe live with it. But the fact that this system has an odd response in the transients and that the dominant pole placement strategy does not work here is important to note. And with tabulation, even though you could increase the number of points, you could increase the interval, it does not really help. But all that we do in dominant pole placement or in tabulation here is we're searching for the best point here that has the best settling time and overshoot values here, but we do not succeed. Now, looking at this root locus here, is it possible, and this is concerning B here, because the question was to propose a PID controller. So can you come up with a better PID controller that at least has the settling time satisfied here? Because we are not satisfying the overshoot, so that's already a problem. But can we do better than this? The actual question is that. Now, you can see that the poles here and the zeros are somewhat close to each other. So, for example, if we pick a higher gain here, for example, something like this, like infinite, then what this would do is that it would get rid of the zeros here. And basically, I'm proposing to cancel out these poles here with the zeros of the controller, because the PID controller adds 2 zeros to this system. And what if we place them on top of these poles here? Get rid of the poles here. Of course, we cannot satisfy the overshoot value, but the tabulation does also not satisfy that. It has an overshoot, but it looks weird and it doesn't work really. It has only the settling time that we're looking for. And my proposal is to get rid of the poles here. So place the zeros on top of these poles. And then we can just mess with the gain in order to get the settling time that we're looking for. And here what would happen is that we would have the settling time line here, and I would choose the gain that roughly places it like this. So basically this would be then the only pole that we would have in the closed loop here. But again, we would not satisfy the overshoot here, but that's also the case for this one here. So in B, what I can do is, instead of doing all the tabulation, all this stuff here, all this line of code, I'm just going to go ahead and place the zeros manually on top of the poles of the system. So let me copy this one here. And I guess that should be it. So we know where the poles are. So what I'm proposing is to place the zeros exactly here. 1, 0.2, 25.01. Of course, I can choose the gain here. Now, before I do that, let me just copy this figure here and show you the root locus. Have that, and maybe also that. So let's also, of course, now let's also not change that. So now we will look at the root locus. We still don't know what this should be and what this should look like. Let's see. I didn't copy this part here, so. There we go. So the poles and zeros in the dominant pole in the dominant region were close to each other. Instead of placing them with a certain distance, what I did is I did get rid of them. I just canceled them out. Now what I have to do is, the only thing left to do here is to choose the p-type controller that's remaining, or the gain here, that results in the pole 2 here. And as you can see, as I move on the root locus, I can see that I have basically a pure integrator in the loop here. Therefore, if I'm having a closed loop with a p-type controller, the only thing that I'll get is I will get k divided by s divided by 1 plus k divided by s. And if you simplify this, you will see that this is basically k divided by s plus k, because I have just s and nothing else. So the gain that I choose is also the pole on the real axis here. So therefore, I'm looking for 2, because if zeta is equal to 1, then 4 divided by 2 gives us 2. Therefore, I need to choose gain 2 here. So this gives me basically the controller. And let me copy this part here. So when we do this, now we can plot the remaining stuff. And there we go. Now, at least this controller has better transients, and it satisfies again the settling time, but has 0 overshoot. And you can see that we are on the same settling time line that is here. So at least I've improved on that, but the next step here is to propose a controller. Now, what did I learn from A and B? So let me also maybe choose figure 2 here. Run them both. So, okay, now in A, we did use tabulation, and the result was not really what we were looking for. And since the complex conjugate poles and zeros were close to each other, I decided to get rid of them. So I've placed the zeros on top of the complex conjugate pole pairs. And then I've just chosen the appropriate k value here that gave me, again, the same settling time here. At least we have zero overshoot, which was also not satisfied in the tabulation method, but better transients because at least we are having a first order like behavior here. Now, looking at figure 1 and figure 2, if I'm going to propose a controller, can you think of a better controller or a root locus scenario where I can meet both the settling time and overshoot criteria? Because I've seen that I should get rid of the poles of the system. I have an integrator because I need that for reference tracking. But what should I do now? We've mentioned about the fact that we should maybe update our closed loop criteria, but we could also update the controller. Now we're trying to update the controller. So what should I do here? Any ideas? It's all about the root locus. So basically, what I'm asking is that I want to be able to choose this point. Therefore, this point should satisfy the angle condition, for example, in order to be on the root locus. Şimdi sıfırları reel eksene koyarsak fakat kutuplardan da bir şey gelecek ve baskın bölgeye 0 yerleştiriyorsun. Yani zaten baskın bölge burası. Yani şunun dışında bir yere 0 yerleştirmediğin sürece işe yaramıyor. Bir de zaten tablolamada bu senaryo ortaya çıkmadı. Eğer iyi çalışan bir senaryo olsaydı tablolamada bulurduk mesela. So the question was what if we place the zeros on the real axis? Now, in the dominant region, we are not able to place zeros because we want to prevent that from happening. Outside of the dominant region is the good place to place some zeros. But in that case, that was not available in the tabulation method, and it's a numerical search, basically. And if it's not possible, then the numerical method does not give that. So if it would have been possible, then we would have ended up in figure 1 with that scenario. So what else? What else can we do? So figure 2 should give you a hint because we are almost there. We did get rid of the poles that were troubling us. We have one pole on the real axis, but what we should really have is to have this zeta omega n intersection here. So what can we do? So what I'm trying to say is basically we have already decided on the locations of the zeros. We have decided that we will have an integrator. So what else? We should maybe add something else to this root locus so it changes to our benefit. Yani leg kontrolörden ziyade acaba sadece bir tane bir şey eklesek de buradan geçse olmuyor mu? Geçmez mi? So what about leg controller? Well, what if we just add something on its own and it'll just automatically update the root locus? Mesela. So what if we add another pole somewhere here on the left? Then we would have one at the origin, one somewhere here. They will coincide and one will go up and the other one will go down. So therefore, and we also know, by the way, where the intersection should be, because we want to be on the settling timeline here. And it's equal to 2 here. The pole here is 2. So they should coincide at 2. And one should go up and one should go down. In that case, and I'm going to show that case in a moment, in that case, I will just look for a gain that assigns the poles to exactly at this point and at this point here. Şöyle, onları zaten ekledik. Yani kontrolör, PID kontrolör olmaktan çıktı bu arada. PID'den yola çıktık. Aslında şu kutupları götürmemiz lazım 0 çiftiyle dedik. Ve PID'nin orijindeki kutbu duruyor. Biz bir tane daha üstüne ekledik. Yani PID artı kutup bir kontrolör öneriyoruz. Böylelikle kutup 0 götürmesi olacak. Orijindeki kutup ve uzaktaki kutup birleşip o noktadan geçecek.
Şeyi sordum ben, bizim proportional değerimiz yukarıdaki şeyi şu şekilde etkileyemez değil mi? Yani sonsuz olsa, sıfır olsa.
Götürme tam üst üsteyse orada bir branch yok zaten. Onlar yokmuş gibi davranıyoruz.
Anladım.
Götürme biraz kayarsa o zaman dediğin problem olabilir. Now, we're not actually using a PID controller, or we're not using some other type of feedback loop on top of a feedback loop. What we do is we just use the PID controller as a base, but we decide that we need another pole in order to have some j omega values in the closed loop. Therefore, we add another pole. And since these pole and zero cancellations are exact in our case, we're choosing them exactly on top of the poles, then the only thing that is left is to decide on the gain that gives us the given zeta and omega and intersection point. And we can also directly conclude the fact that we should add another pole at exactly -4, because we have only 2 poles. One of them is at the origin, the other one is at -4. So they will coincide at -2 and they will go up and down. So let's first try this and look at the results. So here I still choose the same zeros, and I will add another pole to it. Now I can just go ahead and edit here. So 1 and 4. And let's comment this out. 1, 2. And this 1, 2. So the only update is that we have another pole. So this is a 202 pole controller in this case. So it's a second order general controller. Let me update this. So this is the result. Let me also drag these here. Now here we can see that this point is now on the root locus, and therefore we need a certain gain. So I'm going to change it approximately here. So 0.593. So 11.4 gives us the value that we are looking for. So let's open this back up. And there we go. Now, here we can see that the settling time is a bit different. It's not exactly equal to 2. And we can maybe adjust for that, but it's not really important in our case. If we use the zeta value from the formula that is given here, and if you're using omega n equals 4 divided by zeta times ts, then we are happy with that. The settling time formula has a certain accuracy to it, and it has a range for zeta. I don't really remember the exact bounds on zeta, but it has its places where high accuracy is there, but also in some cases it has poor performance. But it's not really that important. Here, the main idea is the important thing, and we can see that approximately the settling time is around 2 seconds, 1.75, and we have 9.92, so approximately 10% overshoot. And we have a nice transient behavior here. So we did learn from the fact that it was not possible to use 2 poles here to get a good result, because we were placing the zeros even more dominantly than they should be. Therefore, we have this interesting behavior, and we decided to change this by getting rid of the poles. So we canceled the poles with the controller zeros, and we added a pole at the origin. Now, at this point, we've seen that actually for a PID controller, for these specifications, it's not possible to come up with a good PID controller. So it's not possible to design a PID controller that satisfies both the settling time and overshoot values here. So it might be the case to update the overshoot here. Maybe 0 overshoot is good for such a system and controller combination, because we are on the real axis if we get rid of the poles. That's a good one. Or we have to update our controller, which we did in this case. So we added another pole. It is sort of a pre-filter type times PID controller. And this gives us the overshoot that we were looking for. Now, up to this point, we didn't really check out what the open loop system looks like or how it behaves, because this is not an ordinary system. This is a special system here that I've chosen for you. Now, this might seem a bit suspicious, because if you look at the denominator of the system, you will see that there is a certain accuracy here. We have 25.01 here and 10.2 here. So we did not calculate what zeta and omega n looks like for this, but remember that 2 times zeta times omega n should be equal to 0.2, and omega n squared should be equal to 25.01. So if I would go ahead and try to calculate what omega n is, I guess it would be 5.01. Is that correct? I'm not sure. And zeta would be approximately 0.2 divided by 5.01 times 2, something like this. So I can see that there's a omega n value around 5, and there's a low zeta value here. So that will become important, because if we have a low zeta value, I know that it will become sinusoidal in some case. And if I have high omega n values, I can also see that the frequency, because 2 pi times f is omega n, f will also be a higher value. So this means that I might have something in the open loop that has a high frequency and a low friction or zeta value here. So that means that the system in open loop, so let's say figure 4, let's look at the step response of GS, because we didn't do that up to this point. Now you can see that it has a very low zeta value. It has around 50 seconds, maybe settling time, and it has a high frequency. Now, this strategy of placing poles and zeros near the j omega axis, or trying to cancel them out, is not also an ordinary method. It is a special filter. Now, if we go ahead and look for the body plot of only this pole pair and this zero pair here, what you will see is that this is basically a band stop filter. So in choosing these two zeros, we've actually used a band stop filter for this system because it has this frequency, this high frequency component. And we've just used a notch filter, basically, to get rid of this oscillation of the system. Now, if we want to see that this has actually an effect on it, what we can do is we can just go ahead and go to 2, for example, here. And you can see in this case, I've chosen the exact same values. The pole zero cancellation was perfect. Now let's toy with that. So let's say that we thought that the poles are here, but let's change the poles here. Let's change, for example, the frequency here. Let's have 24. And let's look at run 2. So figure 2. Now you can see that there's this frequency component in the step response in the closed loop. So if the filter does not do a good job, if it's not band stopping the exact frequency that it should be, then we have these little oscillations in our step response. But by just changing the frequency, by the way, I didn't toy around with the zeta value. So let's try to do this. Let's change also the zeta value. Now again, we see that it has a certain effect. So what happens if we go a little bit crazy? Still, let's maybe decrease the value here, and let's do something like this. I'm just toying around with the parameters. Now, an interesting thing happened here. You can see that the open loop poles and open loop zeros are on the left half plane. So this is on the left, this is on the left. But on the root locus, I can see that there's a branch crossing j omega. And even worse, we have a k value, we've chosen a k value that ends up in instability in the closed loop. Now, this shows us that the pole zero cancellation even near the j omega axis is something dangerous, because we've talked about the fact that we shouldn't cancel out the poles and zeros on the j omega axis on the right half plane, but it's also not really that safe in the vicinity of the j omega. If you're near or close to j omega axis, then this might happen. So therefore, you should be careful with pole zero cancellation, or you should have the exact position of your poles and not that big of a error in your model, so that you can tolerate this error here. You can see we have already a not stable closed loop, so unstable closed loop. So therefore, it's not really that robust to really cancel poles and zeros here. But of course, this is a parameter variation that I've introduced here, so we're not really dealing with them. So you can safely just cancel the poles and zeros, even if they're around j omega axis, because we're not dealing with uncertain parameters in our course. So therefore, it's not really that big of a deal. Just knowing this is important, but you can still apply this in the scope of this course. Now, what we did is, so far, we've seen that examining the open loop is important. And for this open loop system, it's even more crucial.
Burada şu şekilde dönerken böyle dönmesini seviyorum. Onlar da tam olarak oluyor. Sıfırın biraz yukarıda olması
Frekansı arttırdıydım. Düşürmüştüm. 20'ye çekmiştim. Şu şekilde. Tekrar çalıştırayım. Göstereyim. Şöyle oldu.
Bunu önlemek için sıfırı biraz bunun altına yapmaya çalışsak.
Tamam, yapabiliriz ama benim buradaki söylediğim şey şu: biz sistemin kutuplarının şu noktada olduğunu düşünüp tam onun üstüne koyduk. Ama ya orada değilse veya zamanla oradan hareket ederse? Soru o. Yani biraz o. Çünkü şöyle düşün, işte bir motorun modellemesini yaptın vesaire. İşte ısınması, direnç değerlerini değiştirdi ve bir anda kaydırdı gibi düşün. Yani o tarz bir şeydi. Yani çevresel etken, non-linear olması vesaire modelleme hatasına giriyor burası artık. Ya da çalışırken kondisyonların değişmesi.
Mesela hata bölgesini tahmin edebiliyorsak.
Ama işte o dersimizin dışına çıkıyor. Onu söyledim yani. Şimdi bunu söyledim, gösterdim ama böyle bir şeyi biz ders kapsamında şu an için düşünmemize gerek yok. Onun için işte lisans üstünde uncertain parametreler için yani parametrenin oynayabildiği durumlar için kontrol tasarımı apayrı bir ders. Yani o orada inceleniyor. Now, the reason for this branch crossing it into the right half plane or the j omega axis here was due to the fact that there may be some changes in the conditions like pressure, like humidity, etc. And there might be nonlinear regions in our system. The system model may change. So therefore, the system, even though you've designed it on paper, might not work in your, for example, laboratory. So therefore, if there are some parameters that can be changed or that change due to some effects, then this might happen. But we don't really design according to this because this is out of our scope.
Böyle bir şeye karşı sıfırlık mesela ve sınırı eksi 0,5 olacak ve eksi 1'de olacak şekilde koysaydık kazanç arttırır. Sıfıra doğru.
O zaman da şimdi çalışsın. RAM 1'deki gibi basamak yanıtı kötü olacaktı. Yani tabii ki daha sola bir yere koyabiliriz. Ama mesela bunun için çalıştıralım yine aynı şeyi. 20'yi çekelim. Şurayı. O zaman da basamak yanıtını iyi ayarlayamamış olacak. Bunun kararsızlığa gitmemesini umuyorum. Gitmedi. Ama daha da saçma davran. Yani davranışı kötü ama kararlı kalıyor ya da davranışı iyi ama kararsızlığa geçiyor gibi bir duruma düşüyoruz ama bu dersin kapsamında yani kararlılığı önemli değil çünkü biz modeli tam biliyoruz. Her şey lineer, her şey güzel gibi düşünüyoruz zaten. Yani böyle bir zaten bu arada durum değişikliğinden yani ısı değişti işte bilmem ne değişti, basınç değişti o yüzden kutuplar kaydı veya sıfırlar değişti gibi bir durum için adaptif kontrol kullanmak lazım. Yani bunları tolere edecek adaptif mekanizmayı kurup ona göre yapmak lazım zaten. Bir yöntem olabilir ya da bir diğer yöntem bunun aralıklarını bulup o bölgedeki en iyi çalışanı tüm o bölge üzerinden tek tek bakarak denemek lazım. Ama bu tamamen işte dediğim nokta şey oluyor. Ya adaptif diye bir dersimiz var ona geçiş yapıyor ya da uncertain parametrelere göre kontrolör tasarımına geçiş yapıyor. Çünkü o zaman sistemi tanımlarken nominal ve nominalden sapan sistem ailesi olarak tanımlıyorsun. İşte şu parametre mesela delta artı ve delta eksi değişiyor diyorsun. O tüm delta değişimlerine göre bunu nümerik olarak veya teorik olarak ispatlayıp geçiyorsun kontrolörü zaten kullanıyorsun. Ya da adaptif bir mekanizma bu delta ne kadar büyürse ona göre kendini değiştiriyor şekline geliyor. Varsa başka soru şey yapabiliriz. So, yeah, if we are really concerned about such parameter variations, what we can do is we can maybe opt to use this figure 1, so maybe A. Because we have the zeros in a certain safer place, and even though there's a variation, it's still stable in the closed loop. But as you can see, the behavior, the dominant or the transients are looking a little bit more weird there in this case because it's not really our dominant pole placement strategy. Therefore, we cannot really determine the behavior here. But if you're, for example, okay with this, you can just maybe use this here. So now we've talked about A. So let me take this. We've talked about A where we design a PID controller using tabulation. So this might end up in good results, as you can see. But the behavior here is not really examined. During the tabulation method, we don't really look if the system has a dominant placement strategy, if it's having some other peaks. We didn't really look into that, but we just came up with a controller based on settling time and overshoot, and only settling time and overshoot. Here we have learned from the fact that there are some closed pole and zero pairs. So why not cancel them out? It has some advantages, some disadvantages. So based on B, we've proposed another controller that has one more pole to it, and it just satisfies both the settling time and overshoot values or requirements. So
Overshoot özellikle istememizin sebebi ne? Mesela böyle istemem yani. Az önce bulduğumuz sadece o hot zero götürmesi ve kalan şeyde overshoot yoktu. Hani daha çok istenen bir şey olması gerekiyor.
İstenenden ziyade önemsenmeyen durumlar olabilir. Daha hızlıysa overshoot'lusunu seçersin gibi durumlar olur. Yani %10 aşım yapması benim için problem teşkil etmeyen kapalı çevrimlerde onu isterim. Özellikle overshoot yapsın diye isteyeceğim şeyler olur mu? Çok emin değilim senin de dediğin gibi. Yani sanki doğada daha çok böyle overshoot yapmayan, tam oturan işte vesaire gibi şeyler istenir gibi geliyor ama mesela ivme dediğimiz şey veya işte jerk dediğimiz şeylerin overshoot'la yapılması bir problem değildir. Ama daha yavaş ve hantal çalışacağına hızlı çalışması önemlidir bazı şeyler için. O yüzden aşım dikkate alınmadığı durumlarda aşım vardır gibi bir durum çıkıyor ortaya aslında. O kapalı çevrimden istediğimize bağlı veya neyi feda edebileceğimize aslında dönüyor. Ama biz de burada teorik bir konudan bahsettiğimiz için genellikle belli bir overshoot değeri üzerine düşünüyoruz. Ya da bu overshoot'u şey olarak düşün. %5'ler, %4'ler civarında düşün. O zaman da zaten yani pratikte zaten %5, %10 toleransla çalışan sensörlerle çalışıyorsun falan. Hani aşımın da o aralıkta olması problem olmaz gibi oluyor. So for most systems, it seems like overshoot is not really something that is desired, but for example, for some sensors, you might have already 10% variation in your parameters, so you might tolerate that. In cases where settling time is important and overshoot is allowable, then there is a design that might give you some overshoot. There might also be cases where overshoot is really relevant, but I cannot think of one at the moment. So what about the model matching controller? So up to this point, we've used the PID controller or a PID-based controller. So we've talked about the model matching method where we were just looking at the closed loop that should be ideal for us. And in this case, we have already something like that. So we have the system here. So I might get rid of this here. So we have a certain settling time, certain overshoot. We know where the dominant pole pairs should be. What we can do is we can just go ahead and look for the controller that gives us a certain TDS. So here we form basically most of the time PDS, which looks like this, 2 times theta times omega n, and then omega n squared. So this is our ideal pole or polynomial. Now, in this case, what we can do is we can just use an ideal closed loop because this is also a nice closed loop transfer function because it has the dominant poles that we try to achieve here. And I've also placed omega n squared in the numerator because I wanted to get a closed loop transfer function that has gain 1 in steady state. So if you plug in s equals 0, these two have s in them. So therefore, we will end up in omega n squared. So omega n squared divided by omega n squared gives me 1 in steady state. So therefore, I've chosen this desired closed loop transfer function. Instead of choosing the controller itself and then looking for the closed loop, what I can do is I can decide on the closed loop and try to come up with a controller that achieves that closed loop. So that's basically model matching controller. And if you remember, or if you don't, I can just quickly recap. So since fs times gs divided by 1 plus fs times gs is the closed loop, what I can do is I can plug in TDS here instead of TS, and I can try to come up with the expression that gives me the controller here. So if I multiply that, I get TDS, and then we have this here. So I can rearrange stuff here. I want to get rid of, or I want to find an expression for fs. In this case, you can see that we have gs in both of them. And so let's divide by gs. So let's get rid of this. And then we have fs here. So this would become 1 minus TDS, 1 minus TDS times Fs, and then finally I'll get this here. So if you have a certain closed loop transfer function, you can use TDS divided by 1 minus TDS times GS as the controller itself. Now here we have GS in the denominator, and that's really important here because if you think about it, we have something like this here. So let me get rid of this. Basically, we have times 1 divided by GS, something like this here. And this 1 divided by GS will be then calculated, or will be multiplied with GS. So at this point, if we plug in this here, we'll get a pole zero cancellation, basically, or we cancel out all the poles of the system and all the zeros of the system with the controller poles and zeros. So therefore, if the pole zero cancellation is not exact, then we are basically in trouble for this controller because it is based on this cancellation. If that works, then my loop transfer function will be TDS divided by 1 minus TDS, and then if I calculate the closed loop, I'll get TDS eventually. If the pole zero cancellation is not exact, I'm not really matching the poles and zeros of the system, so therefore it will not match. So that model matching controller is actually referring to this pole zero cancellation here. So since we know how to calculate the controller, let's quickly do that. So TDS divided by 1 minus TDS times GS. So if you calculate this, you'll get a bunch of poles and zeros here. Let me show you. As you can see, it seems like this is a fourth order controller, but in reality, this is your controller. And you can see that this polynomial here is in the denominator, but we have also the same here. So there's a cancellation, but MATLAB didn't really got rid of it. So we should use the minimum realization here, which does the pole zero cancellations. After that, so looking for ZPK of Fs, we can see that we have actually the same controller that we've tried to design in the previous part in C. So the controller that we've proposed is actually the same controller that is given with the model matching controller here. So we have again S, we have the denominator of the system, the notch filter part. We've added the pole at 4, and we also have chosen 11.4 roughly as the gain of the controller. So it is basically the same controller. So a model matching controller has given us the same result. This means that, and it is also really important that model matching controller can also be sometimes a good thing because it gives you an idea about the controller structure that you might want to use. Because it also shows you that if PID controller would have sufficed, it would have given you a PID controller, but it didn't give you a PID controller. It gave you a PID plus 1 pole as the controller that is ideal for the system because it exactly gives you TDS here. So it gives you the dominant pole pair with infinite dominance factor because there are no other poles and zeros. Everything is canceled. So this is basically the ideal case. In some cases, we might want to use a dominant pole placement, but in other cases, it might be also a good idea to check out what the model matching controller gives us.
Bu şekilde bir sonuç vermesi aslında ileride PID açısından daha iyi gerçeklenebilir.
Gerçeklenebilirlik model matching kontrolörün aslında sağlayabildiği şey olmuyor genellikle. Bu sistem için özel bu şekilde çıktı, gerçeklenebilir çıktı. Ama normalde gerçeklenebilir çıkmıyor. Çünkü yüksek dereceli kontrolör verecek garanti neredeyse. Şöyle düşün, 4. dereceden bir sistem olsa 4 tane sıfır ekleyecek bir kere baştan. sonra bir de o kutup ve sıfır çifti eklemesi durumunda daha da kötü olacak. Gerçeklenebilirlik pek bu kontrolörün yapabildiği bir şey değil. Ama bu durumda evet, daha gerçeklenebilir bir şey verdi. Gerçeklenebilir bir şey vermesinin önemi çok da hani PID kontrolör konusunda problem değil. Çünkü PID kontrolörün D kısmı özellikle bize problem çıkarıyor, türev kısmı. Onu yaklaşık türevle zaten çözüyoruz. Yani şöyle bir şey yapmak mümkün. D yerine, yani işte KDS yerine, KD çarpı S zaten Simulink kullananlarımız otomatikman yapıyor, farkında olmayabilir. İşte N çarpı S artı 1 gibi bir yaklaşıklıkla, N dedim çünkü Simulink de bu kullanılıyor. İşte ne bileyim 0.01S artı 1 gibi bir şey. KDS bölü 1 değil de KDS bölü işte 0.01S artı 1 gibi bir şey kullanıyorsun. Türev yerine yaklaşık türev kullanıyorsun. Bu yaklaşık türev de zaten nedensel olmuş oluyor. Dijital tarafa geçtiğimiz zaman işte ileri fark, geri fark olması mevzusu. İleri farkın teorik bir şey olması bizim geri fark kullanmamız ona türevi yakınsamak için. Aslında ona dönüşüyor yani. Now,
Biz geçen dönem Emre Hocam'ın dersinde şey yapmaya çalışıyorduk. Akciğerle alakalı bir türev almaya çalışıyorduk. Türevi alamıyorduk. İntegral üzerinden olmuştuk. Sebebi olmuyor. Türev hata veriyordu.
Yani integral üzerine daha yumuşak bir türev almışsınızdır. Belki o yumuşaklıkla da alakalı olabilir. İntegrale alınıp türevi alınmış bir sinyal, normal türev alınan sinyalle daha yumuşak olabilir. Belki öyle bir şey olabilir. Ya da back difference'e karşılık geliyorsa o da olabilir. Ben şimdi tam oradan emin değilim oradaki kullanılan şey. O zaten Z transformunda şeydir muhtemelen. Yani back difference'a denk gelecek şekilde almak zorundasınızdır muhtemelen. Ya da nümerik türev olsun diye. O da zaten back difference, başka bir şey değil. Now, isn't it, the question was, isn't it a good thing that we have a realizable controller here? For this system especially, this is the case, but for most of the systems, the model matching controller does not give us a realizable controller. It gives us a high order controller. And we can think about for example, fourth order system. If we had a fourth order open loop, then there would be 4 zeros in the numerator and then some poles in the denominator, which would make it hard to realize it. And for example, the PID controller is not really that bad because in real world applications, most of the time, we don't really use the derivative directly. We use an approximation for it, or we use a filter times the derivative. So therefore, we are not really that much in trouble if we have a PID controller. Now, so this has shown us that we can use the model matching controller to get an idea about the controller that we should choose for a system, for example. But as I've shown you, it's not always a good idea to cancel out all the poles and zeros because it might be around the j omega axis. Then we would maybe end up in a unstable closed loop. But for certain cases, it really works well. For certain cases, it does not. So we should basically look for the model matching controller solution and for our own solution, maybe decide on that, on which one is better, which one is worse. So in the notes, by the way, I have given you the solutions, but instead of using MATLAB to solve the algebraic problem here, I've given you something that is in your notes where you can just state the function, the set of equations in matrix form by choosing the desired polynomial coefficients and the residue polynomial coefficients here. You end up in a matrix problem. You can just look through this example. And the general form here is this, where you choose ki as the free parameter. If you remember, we had a three equation, four unknowns equation set. In this case, it assumes a more general form for the residue polynomial here, E1 and E0. So E1 S plus E0, where we've chosen it already S plus P. But E1 will end up being equal to 1, as you can see here. So therefore, it's not really that relevant. And this is exactly equal to P, if you remember. It was 0.087 Ki, something like that. So for exams, it might be a good idea to check this out because you might want to use that. But the downside here is that for a 4x4 matrix, so 4-column, 4-row matrix, it's not really that simple to take the inverse of such a matrix. But maybe Gauss elimination or some elimination might help you out. Sometimes it's good to just use the direct coefficients. Sometimes if it's a 3x3 or 2x2, just take the inverse of this matrix here. So up to you. I've just provided you an example here. And then with the solution here, I've also provided the zeros and all the stuff that might be filled into the table. But the important part here is that we have such a result, and it might be possible to opt for direct and exact pole zero cancellation. But both this one and this one corresponds to a certain bandpass filter. At this point, if you have an exact pole zero cancellation, you don't really see the effect of the bandpass filter. But if you have this, then it has a certain quality factor to it and a certain bandwidth to it. So that affects the system's response in closed loop. And then we've also seen that based on the previous examples, we might add one pole at -4 so that they coincide at -2 and one of them goes up and down so that we can choose the point that we are after, where zeta is 0.59, and then we have also the corresponding omega value. And we've seen that the model matching controller gives us the same results, which is not really that surprising for the system because this is the best we can do. So that's it basically for this week. I don't really remember what next week was, but we will continue on our discussion in time domain methods. And that's basically it.